So let us begin the class and then share the screen and uh, sort of, what is it? Can all of you see the screen and hear me?
Yes, sir.
Yeah. So questions from the last class. Essentially, we were talking about elasticities, and I was trying to tell you that the idea of elasticity is really a very simple one. You're all familiar with the fact that when y is a function of f of x, then the change in y with respect to change in x is given by dy by dx. But if you want to look at percentage changes or fractional change in y over fractional change in x, and that's what I was saying, percentage change or fractional change in x, then really it is the elasticity E of y with respect to x. And the reason, I mean, many of these things that I want to teach you, elasticities, for example. Now, of course, we will apply it to enzyme kinetics and to system biology situations where A is going to C and so on and so forth, and try to see what is happening in networks when enzyme concentrations change here or enzyme concentrations change here, what happens to B, what happens to A, and so on and so forth. Or when B changes, for example. And so we want to look at networks where changes, how these perturbations go, and therefore it is important to look at percentage changes. But like any other concept, the concept of elasticity has very wide applications. And I hope you realize this. I mean, well, a large number, a significant fraction of your class will possibly move to finance or management at some point of time. And then, then you will discover that actually we are also looking at elasticities of supply and demand. And how is, and if you're producing a product in microeconomics where you are saying that the cost of a good, the price of a good is, well, again, started the same problem. Very early in the day. Can you hear me? The price of a good is a function of, say, two variables u into v. One is, say, the amount of raw materials and the cost per unit raw material. Then if you can reduce raw material amount by, and this is, say, raw materials and amount, and you can somehow reduce the amount of raw material, the amount and this is the price of raw material per unit amount, and so the total production cost is impacted both by the amount of raw materials used and the price. Then if there is a fluctuation, then the elasticity is a sum of the fluctuations, not a multiple. So the percentage change in the cost of production would be a function of the percentage change in raw material cost amount and into plus the variation in price, and so on and so forth. So when you learn this in microeconomic theory or in terms of supply and demand, again, elasticities play a very important role. So all these concepts that one teaches you transcends the requirements. These concepts transcend just the basic course, and they have applications elsewhere. And therefore, sometimes I feel a bit, sad that many of your colleagues feel that they don't need to attend these courses because what you learn in your BTech program is more than just biochemical engineering. You learn concepts which have wide applicability elsewhere. Tomorrow in management, they will teach you the same stuff with a lot of mumbo jumbo, and hopefully some of you will realize that this was taught in a single class in enzyme engineering. But yeah, let us go ahead. For example, when y is a function of two variables u plus v, I mean, let us take a very simple example of costing. Again, the price of production of protein, we are talking of protein production, which we now remember, for example, depends on upstream cost or fermentation costs. Let us say fermentation costs, because upstream plus purification costs. And it turns out that fermentation costs usually, because of highly efficient fermentation, is, say, 20% of the cost, and this is 80% of the costs. Now, the total cost is like this, the total cost. and you go to your company boss and say, well, you know, I have improved this, and a lot of people, scientists do this. I have improved fermentation efficiency by say 10%. And you say, well, that reduces the cost by 10%. No, it does not. It reduces it by 2%. Because as you remember, we talked about the fact that the elasticity of a function, so E of y will be a function, and that makes sense, right? Because, you know, if you change this from 20% to 18%, the total cost becomes 98%. That is very obvious. But it's also true that E of y is E of u into u upon u plus v. That is why it makes sense, right? Or y. And so this is the fraction into the percentage change. So it's really simply a arithmetic average, some kind of average, weighted average, plus E of v into v upon u plus v. So this is an 80% fraction, and this is a 20% fraction. And so if you change this by 10%, then you would have changed the effective costing by 8%. So oftentimes we tend to sort of in industry, we are very conscious of the fact that what is the process that you're optimizing? What is its contribution to the total cost? If it is already damn efficient and it is only 20%, then, you know, don't touch it. Touch this one. Don't touch this price. Try to look at purification rather than fermentation. Even though fermentation can be improved very easily, the management is not interested because the cost is already 10-20% or maybe even 10% of the total cost. And that is why, and a more funny remark would be that, you know, in industry, I mean, one has worked there for a long time, we are told to produce, the costing is the total production cost should be 20% of the sale price. You know, nowadays with efficient industry, the total cost of production, the total cost of production has to be 20%. Sale price is 100. So therefore, the remaining thing is all taken up by the service sector, which ensures various increases in price. And that is why, you know, many of you move from engineering to management, because this is where the money is, the remaining 80%. If you can make this more efficient, and that is what Amazon did, you can touch this factor much more efficiently, because improving efficiency of production from 20%, even if I improve it by 10%, it's an already efficient system, I only impact on the sale price by 2%. But if I can change this and cut out middle management, middle level people for distribution, I actually save much more money. But that's another story. So sort of telling you some of the interesting examples that we can extend from the whole notion of elasticity. It's very interesting. I mean, you know, you should think about these things also. When you, for example, the whole thing that I talked about, and nobody asked a single question, and I was a bit surprised. This whole notion of relaxation times is a very, very important concept in modeling, and in a huge range of subjects. Again, borrowing from a very crude and a rather simplistic use of relaxation times, it's actually used much better in time course studies where systems have different relaxation times. But think of short range profits, just sort of because you seem to be, BTech students seem to be more interested in management. I'm using these, but really I have no very major interest in it, even though I have worked in the industry for a long time. Or short range profits, or medium range profits, or long range profits. The short range profits are driven by innovation, but long range profits are driven by the state of the economy. The state of the economy is actually considered to be in its initial state because it has large relaxation times. So when you're looking at short-range profits, you're looking at innovations in the short term, which actually increase the profits. But for economy for long-run profits, you have to look at what is happening. How are the economic changes taking place in the whole country? So economy is impacting on long-term profits, but economy has no impact on short-term profits, because the relaxation times of the economy are way larger compared to the innovation timeline and the short-range profit, the window in which you are looking at it. Your window of observation for short-range profits is too small, and these are very, very large relaxation times. And so, you know, you have a very, very interesting set of applications, and this, of course, I borrowed from a very simplistic economics, though these seem to be nowadays virtually important, but complex, interesting, and very interesting research problems utilize concepts of elasticity and relaxation times in much more complex ways, which I will not get into because this is an enzyme engineering course. But I always want to sort of mention these from time to time to give you a flavor of what is happening in the world and how concepts interconnect across disciplines and therefore have a life which transcends one single subject. And that's something which with time you will become aware of, the interconnectedness of concepts. So yeah, just let us get back to our work at hand. So really, let us now get down to back to our old problem, mass action kinetics. Before we start into enzymatic kinetics. Now, mass action kinetics, simple enough. What was it? Now you can tell me what was V is equal to for A going to B. Simplest case. What was it equal to, or S going to P? Okay, with by mass action kinetics, it would be K1S minus K2P, right? Some response, some questions. I would be and I defined rho as the VR by VP, VR by V forward. Sorry, V not VP, VF, right? Now, what is the elasticity of, let us say, V by S? Please, some comment. What is V by S? मुझे भी याद करना है कि लास्ट क्लास आपको याद है कि नहीं, क्या होगा? Hello, can all of you hear me? Let us say yes or no. Can you hear me?
Yes sir, yes sir, yes sir.
हाँ, तो बताइए क्या होगा? ये फंक्शन है, ये fx is equal to ux plus gx, ux plus vx और gx plus hx. मैंने क्या लिखा था? मैंने gx plus hx लिखा था. तो क्या होता है इसका elasticity? The elasticity of this into
into gx by gx plus hx.
gx plus hx. हाँ, तो elasticity of k1s क्या होगा? K1s elasticity आप लोगों को पढ़ाया था भाई, ये तो सिंगल फर्स्ट ऑर्डर फंक्शन है ना, तो इसका elasticity क्या होगा? K1. भाई आप रूल्स भूल गए क्या आप लोग, है ना? So a function, I mean, you see, a first order reaction given by ds by dt is equal, or v, which is defined as v, is equal to k1s. ये फर्स्ट ऑर्डर फंक्शन है ना, तो ये k1s है.
Yes sir.
है ना, ये v है, ये s है, ठीक है ना? तो इसका स्लोप क्या है? दिस इज dv by ds.
1.
So ये है, और इसका v by s क्या है? 1. So your elasticity is not k1. It is, that's what I wanted to say. Somebody say that this is wrong. Nobody pointed out. So the elasticity is 1.
1.
Okay. हाँ, ठीक है ना? Remember, it is n when it is, if this was k raised of n, then E would be E of v by s, or v by s will be equal to n. ठीक है ना, अगर ये ऐसा होता तो. Now this is 1, elasticity is 1, so into this function upon
minus k2p.
Yeah, sorry, something again gone wrong. Can you hear me, or is this says bad network quality? Can you hear me, both of you, all of you?
Yes, sir, we
Yes,
can
sir.
hear you.
Yes, sir.
This is it. Okay, and now at least you can tell me. And so this is equal to what? This is equal to, in terms of, it's simply vf by v, right? Or if you want to write it, vf upon vf minus vr. Or in terms of rho क्या होगा ये? Remember, rho is this. इसको in terms of rho बताइए क्या होगा? divide by VF and you get what? 1 upon and divided by VF, what do you get?
minus 1 minus rho.
Minus. ठीक है? Okay, and so 1 upon 1 minus rho, and what about E V by P? What is that equal to? By the same formula method,
minus 1
into K2P
into
upon
E.
K1S minus, which is equal to minus VR, go on, upon VF minus VR, and in terms of rho, minus, and now you have to divide by,
1 upon
बहुत, हाँ, तो फिर वो एक स्टेप और करिए, आप VR से क्यों डिवाइड कर रहे हैं? VF से डिवाइड करिए ना, क्योंकि ये VF है ना,
Yes, sir,
तो 1 upon 2 लाना पड़ेगा, VF से डिवाइड करिए तो क्या हो जाएगा?
minus rho.
माइनस
Minus
रो,
rho
हाँ,
upon 1 minus rho.
upon 1 minus रो, ठीक है ना? So can you notice something very obvious, that this and this, I mean absolute values नहीं लेना चाहता हूं मैं, this plus this क्या है?
1.
So this is 1. So EV by S plus EV by P is equal to 1. So this is one formulation. So for inverse action kinetics, this is one formulation, right? Right? And also notice, what about the absolute values? Can you say something about the absolute values? So which is larger? So I'm asking you that what about mod of EV by S?
Sir,
Is this large? I mean in terms of
larger.
magnitude, because it's negative है ना? ये
It
1
will be
है,
larger.
ये rho है. Rho is always less than 1 divided by 1 minus rho.
Yes, sir. So like EVS is greater.
EV by S is always greater than EV by P. ठीक है ना? And also, obviously, very obviously, what about EV by P divided by EV by S is equal to minus. ठीक है ना?
Yes.
The ratios is equal to minus rho. Is this not true? Good. And all of you hear me? So minus rho, ठीक है ना? So these are some of the basic formulations, right? Very obvious, simple algebra. And now let us actually plot this. You remember all this? And so I mean, and I'll plot this. ये मेरा आवाज हो रहा है कि आप में से किसी ने ऑन कर रखा है? Anyway, so let us actually do it slowly. I mean, let us do it the way I do it for MSc students. Don't get upset by it. Let us do it slowly. So tell me, let us take row values, and then you tell me EV by S, and you tell me EV by rho. And then, so let us take, remember it has to be less than 1.9, and let us say what, 0.5, 0.4, 0.2, 0.1. Let us do this. What do we get? Come on, EV by S. What is EV by S?
10.
10.
10. EV by rho? EV by P, sorry.
-9.
-9. Obviously, because they will. This is the basic equation that has to be worked, right? This plus this is equal to 1. 10 minus 9 and 0.5 पे क्या होगा?
2.
So 2.
2 obviously. हाँ, आप लोग थोड़ा स्पीड बढ़ाइए. Sorry. Okay. Then 0.2. ये हाँ, and so on and so forth. 0.1 में क्या होगा? 0.4 में क्या होगा?
1.6.
ये क्या है? ये 1.6 है. मैं कैलकुलेट नहीं कर रहा हूँ. I'm hoping that this basic arithmetic should be easy enough and family. Basically, you have a very simple formula. This is the formula, na? 1/1 minus
Yes.
0.4. So 1.66.
Yes.
And this will be minus 0.66, right? By definition.
Yes.
And 0.1.
1.1.
1.1, and this will be.
1.1.
यार क्या है ये? This is absolute nonsense. Can you hear me still? 1.1 and minus.
Yes, sir. I can.
Yes, sir.
Minus 0.1. ये तो हर something very seriously wrong with my laptop. Oh, I've rubbed out everything. Anyway, it's fine. That's all right. So really, now, all that was not really necessary. Really, what I want is a plot. Let us say this is row. I don't know the blocks plot here. And you should, as I told you, I failed in my engineering drawing, so you should assume that I cannot draw anything. And let us say that row goes from say 0, almost 0, to say, let us keep it 2 or something, or 3 or whatever, 2, right? And this point here is 1, because that's why I want to keep it 2, because they're equal. The row is 1 is equilibrium, right? I hope you remember that. And let us plot this as elasticity. And let us first do EV by S. Okay. So what is EV by S? How does the plot look like? Suppose it is 0. What is now you have your, I mean, I'm not going to show the display, I hope, and I told you that you should take notes. So how does the plot look like? 0 पे क्या होगा? Elasticity?
1.
ये 1 होगा, ठीक है ना? So let me call this 0 and let me call this say 20 or something, and this is, let me call this as minus 20, है ना? तो यहाँ से शुरू होगा. And as it goes to 1, how does it go? It keeps going up. As a matter of fact, at rho is equal to 1, this will go to infinity, right? 1/1 minus rho, essentially, a very simple plot, right? What about when rho values are greater than 1? Of course, at 0 minus, at 0 plus it is plus infinity. At 0 minus, you will notice it will be minus infinity, right?
Yeah.
And as it goes up and up, as rho values go, and it will be minus infinity. As it goes to 0, it approaches. As it approaches very large numbers, 1/1 minus rho approaches 0, right?
Yes.
So ये asymptote है 1 का और ये asymptote है 0 का, ठीक है ना? So this is EV by S. This is EV by S. What about EV by P? What about values of is equal to 0? Minus, what was it?
Will be negative of that multiplied by rho.
So it is minus rho.
At 0 it
So
will be minus rho.
0 will be 0. Right? 0 will be 0. 0 at rho equal to 0, it will be EV by S will be 0, right?
Yes, sir. Yes.
Yes, sir.
Just numerator is 0. The denominator is not 0, so it's all right. 0/1 minus 0, right? And as we increase it to 1, again it is going to minus infinity.
Yes, sir.
Oh, sorry. I mean, notice that this function plus this function is always equal to 1. Right? This plus this is always equal to 1. So this is 1, this is 0. This is 10, this is minus 9. This is 20, this is minus 19. This is 200, this is minus 199. This is 1000, this is minus 999, and so on and so forth. Right? Because of this very definition. What about on the right side? The right quadrant kaisa lagega? This is going to 0 at minus infinity because this is approaching 0 from the left side. From here it will go like this. Right? So this is going to infinity. ये कहाँ पे asymptote बनेगा? 0 पे बनेगा, भी 1 पे बनेगा?
1.
When rho is very, very large, when the rho is very, very large,
0.
then it is 0. So you notice that it is going to go to 0.
So, sir, the black curve that will be like there.
Yeah. I can't hear you, Ratnesh. But always remember that this plus this is always equal to 1. So notice that this is a very interesting situation here, that the sensitivity of the system is extremely large at rho values close to 1. At near thermodynamic equilibrium, you have a very serious problem of sensitivity, and that makes sense because reaction rates are close to 0. They're close to 0 because the forward and backward reaction rates are matching. Because the velocity v at is equal to Vf minus Vr or K1s minus, but if they are close to equilibrium, small changes in non-equilibrium values, small changes in S is actually going to have a huge impact on the velocities because the sensitivities are very, very high. The elasticities are very, very high. And when they are far from equilibrium, then the elasticity is not impacted significantly. Okay? So the problem of course, when rho values are less than 1, this is the forward reaction rate. This zone here is the forward reaction. Makes sense because this is positive, this is negative. So it is forward reaction. And this part here represents the reverse reaction taking place because rho is greater than 1. So we talked about this in the last class, that negative values of rho, because rho is nothing but the mass action ratio upon the equilibrium concentration. So when rho is less than 1, the B is, or the P is less than S in terms of equilibrium concentrations, and this is P equilibrium upon S equilibrium. So therefore, this is the forward part of the reaction, this is the positive rate, and this is the negative rate. Does that make sense? And you can also see that I can extend this very, very quickly to nth order reactions. For example, if I were to sort of plot the typical N1 A1 plus N2 A2 kind of thing, and plus whatever is giving backward reaction M1 B1 plus M2 B2, something like that. Remember I wrote that? Then what is my elasticity with respect to A1? What is EV by AI, let us say? What is it?
It will be Ni.
Ni, right? So it will be Ni, and therefore it will be, so the AI forward will be Ni upon 1 minus rho. And similarly, EV by Bi will be what? Rho Mi upon 1 minus rho. Did I now jump too much or does it make sense? इसका आप कर सकते हैं? Does it make sense?
Sir. Yes, sir.
Yes, sir.
Does it make sense? All of you? Yeah. I mean, I sort of jumped a step because I was getting bored with keeping it too simple. Okay. So now notice that similar plots can be made for such reactions. But the essential argument remains the same, whether S is equal to P, a very simple unimolar elementary kinetics, that the sensitivities are exceptionally high at values of rho close to 1. Really, that is what I'm trying to sort of emphasize here, right? So, I mean, let us sort of, not go further ahead, but I'm sort of trying to say that let us do other kinetics and find out. So this was a very simple enzyme kinetics. Let us look at other kinetics. For example, one of the common things, I think even Arunangshu mentioned this, is the Hill equation. V is equal to V max SSR of n upon Km plus SSR of n. This is cooperative equations very often, and I'm sure you have studied some biochemistry where they would have shown you this, right? Did they teach you biochemistry? ये V versus S का plot? ये ऐसे cooperative binding ऐसे करके plot दिखाया था आप लोगों को? Hill equation biochemistry में पढ़ाई है? Yes? No?
No, sir.
Oh, sir.
ये कैसे हो सकता है भाई? Hill equation नहीं पढ़ाया?
No, sir.
आप लोग भूल गए हैं कि मतलब there is general
No, sir. Like they didn't teach us.
They didn't.
No,
Very
no,
unfair
sir.
of them. So this is called cooperativity, and the fact that as enzymes bind to the substrate, the enzyme rate increases. So this is cooperative. You would have negative cooperative, positive cooperativity, and I was going to ask you about the n value because there are 4 molecules which can bind to this enzyme and make it more and more efficient. But it turns out that therefore models should predict that n should be equal to 4, but it turns out that experimental values make n equal to 2.8. But all those things I will come back later. Maybe I'll have to teach Hill equation again, enzyme kinetics. But really, so what is the, okay, now let me, a simple task, EV by S of for the Hill equation. I will let you do it. इसी तरह के एग्जाम में आएंगे सवाल सिंपल टाइप के आप लोगों को नहीं और शुड आई मेक इट मोर कॉम्प्लिकेटेड एनीवे लेट अस derive the cooperativity for using the rules that the summation rule, the multiplication rule, the division rule and the power rule. So for example, I will break it up into the first step. This is EV by S is E of Vm SSR of n minus E of Km plus SSR of n. And so you can do it stepwise if you want to do it. And this is E of Vm plus E of SSR of n. And minus this, let us say, same thing. And so on and so forth. Please do it by simple log rules. It is essentially like a log rule. Only thing is when it is something plus something, then you have all these issues. So when you have this kind of formulation, you have to be careful. You have to say EKm into Km divided by Km plus SSR of n and E SSR of n. So this here will be EKm into Km upon Km plus SSR of n and plus E of SSR of n into SSR of n divided by Km plus SSR of n. चलिए बताइए क्या होगा मुझे.
So like S to the power n, you can just make it n into.
SSR of n is n of E raised of S, which is 1.
Yes, sir.
So it's just that makes. I mean, we can do it by formula, or it's obvious rather. I mean, I just sort of mechanically using the formula to do this. Please go ahead and tell me the answer. ये सब algebra मुझे नहीं आता. आप लोगों से मैंने कितनी बार कहा. We are all not old. Because this is where I will sort of stop elasticity, teaching elasticity, and move on to the next part of the course, which is actual enzyme kinetics. So you did derive, I hope you remember the derivation for E V by S for simple enzyme kinetics, which is V is equal to V max S upon Km plus S. इसका क्या था? I hope you remember. It was 1 minus, क्या किया था हम लोगों ने? 1 minus S upon Km plus S था ना ये, which was simply equal to Km upon So the E value is Km upon Km plus S, which I said made a lot of sense because for S being very small, S much smaller than Km, it's a first order reaction. So this expression here becomes equal to 1, and for S much larger than Km, E becomes equal to 0. So now I want you to find out for the Hill equation. क्या है भाई, आप लोग बताइए आंसर. अब में से कोई भी नहीं कर रहा है, मतलब all relaxing and watching. मतलब are you in bed or something that you know you are sort of little सुना जाए. करिए.
Km plus Sn.
हाँ, एक जना तो बता रहा है. Good, thanks. What is it?
N Km
N
divided by Km plus S raised to the power n.
N Km plus S of n.
Sir,
Is
n
this
is
what-
also multiplied by Km. Numerator.
Sorry.
Sir,
N is
in
also divided by K.
n is multiplied by Km in numerator.
Okay. Km into n. है ना?
Yes.
So all of you are getting this? So
Yes,
E is
sir.
equal to
Like
N Km upon Km plus SS of n. All of you got this expression? Which is essentially just like this, Km upon Km plus S. यहाँ पे एक n आ गया. All of you can hear me? So it is exactly like
Yes,
this.
sir.
Here there's one n and here there is one n. Right? And that makes sense, right? So the Sn comes in the numerator because the numerator is now no longer Km plus S, it is Km plus S of n. But this Km here remains Km, but it gets multiplied by n because, as you know, that power equations, the moment there is an n here, there is an n here, these n's here sort of get incorporated here. And so, as you can see, in the Hill equation, the sensitivity to substrate changes is n times higher. That makes sense to you, right? Because the cooperativity then allows the enzyme to respond much more sharply to substrate concentration changes than the response of a normal substrate change. As you can see that in normal enzyme kinetics, the maximum elasticity that you can achieve is 1. It is usually less than 1, but since S values are very small compared to Km in real life, and that is why, you know, I will talk about the fact that binding efficiencies are very important. So because for all practical purposes, V is equal to Vmax S upon Km plus S, and therefore, and since S is very small, then this basically denominator translates to approximately Km. And so usually we have first order reactions taking place inside the cell, inside the body. For all practical purposes, S values are not very large. Obviously, why will the body maintain high concentrations of substrate when it has an enzyme to digest it? So if this is small, as a first approximation, V is actually first order with the rate constant being Vm upon Km. So this is being approximated as Km, and so into S. So the first order rate constant K1 is actually Vmax upon S, Km. So it is Vmax upon Km, which is a far more important parameter than just Vmax. So both rates as well as binding efficiencies play a very important role in enzyme engineering. So Vm, and so this is just a first order reaction which is equal to Ks, where K is this at the lower value, and therefore sensitivity is 1. But the Hill equation now allows you for example, low values of S, a sensitivity of N. For low values of S, you can see that E would become equal to N. Here, E was maximally equal to 1. So, N times faster response to changes in substrate concentration because of cooperativity in the enzyme kinetics. So, we'll come to these things later on. Is this all clear? So, shall we sort of stop this subject here and we will use elasticities in a range of places. But let us, we have wasted enough time, as I would say, not wasted, but this was all essentially background. And let us now get on to enzyme kinetics itself. Shall we start today? I mean, after all, we have.
Yes, sir.
Yeah, let us get on to enzyme
Sure.
kinetics. So let us begin by the simplest of things, that how do enzymes work? They work by binding to the enzyme, and so the simplest way of understanding enzyme kinetics is by looking at what are the elementary reactions that are taking place. So the elementary structure or the elementary kinetics allows us to derive elementary rate equations, so the elementary reactions. And this is something which you all know, but sort of mention this, that actually the enzyme binds with substrate. And again, as I said, I use relaxation time concepts. We'll begin with the simplest of models, that there is a time in which it sort of reaches steady state, and those times are very, very small compared to rates of reaction. But this sort of binds to the enzyme substrate complex, right? And the forward reaction is K1, and the reverse reaction is usually called K minus 1. Because we say that the enzyme substrate complex is not only sort of associating and dissociating with respect to enzyme and substrate, but also getting converted to Can you hear me?
Yes, sir.
Yes, sir.
Yeah, it is getting converted to E plus P, and this here is 1 and this is not 2. Why do you think that is so? Because remember that your substrate is like this. This is S, this is P. So this constant, unless P is somewhere here, if the P was here, then I would write it as this. But if P is here, then the enzyme substrate complex will dissociate to E plus P, and the reverse reaction will not be important. So whether this thing exists or not depends on what is the delta G of the reaction, and we will address delta G's and kinetics later on. Let us start with the simplest case where this is absent and this is just K2. Okay, and the dissociation constant is Kd, which is given by minus K minus 1 upon K1. And I will make it more complex as we talk about. Let me not introduce the complexity right away. It impacts on my teaching efficiency and learning efficiency. So this is the dissociation constant of ES with respect to ENS, and so this is simply nothing but the product. Okay, ES. I'm talking of dissociation constant. So E and S are on top. Association constants, it would be on the other side. Okay, does that make sense? And we will work with dissociation constant because it simplifies the algebra enormously. It is an approximation, and why it is an approximation, I will tell you later. It's obvious. So I will work with dissociation constants, which is nothing but ES and ENS. So the enzyme is either here or here. It's also here, but I'll come back to that. So this relationship is very important. What is the relationship between ES and E plus S? And that is simply given by the dissociation constant E into S upon ES, right? And now we have a very simple method. We say, what is the total amount of enzyme? The total enzyme of enzyme is either free enzyme or bound enzyme. It's either free, because this is regenerating the enzyme and it's being used back here. So the total enzyme that you have added in a reaction mix is either free or in the bound form. Does that make sense? Okay, so it's either free or bound.
Yes.
The total enzyme that we have is ES. And so E, the free enzyme, is simply equal to the total enzyme ET minus ES. Okay, so KD, for example, can be written as KD can be written as, for example, ET minus ES, I'm not putting two brackets again, into S, E is this, right? So this is obvious here. So this is E here, into S, upon, so we are doing very, very simple algebra here, upon ES. Okay? And so we can do all kinds of things here. So I mean, I can write it any way you want to, and really what I want to say is that I can do other kinds of algebra, but I will not do it, or maybe we should actually. So just for just multiplication division, ES upon ET minus ES. So this upon this upon this, ES upon ET minus ES. This sorry, ET minus ES is equal to S upon KD, right? ES upon ET minus ES is equal to S upon KD. And so on and so forth. You can sort of just keep on doing this algebra, but I'm not really interested in all that. Really what I'm trying to tell you is that the velocity of the reaction, what is the velocity of the reaction? It is equal to K2 into ES. Does that make sense?
Yes, sir.
So the rate of reaction is simply this. But ES is something which you do not know. What have you added in the reaction mix? You have added ET, this here. So you want to express ES in terms of the total enzyme that you have added and in terms of S, because that is what you remember. This equation here, this E is not E total. This is E interacting with substrate, free enzyme interacting with substrate to generate an ES complex, and that free enzyme, that ES complex has a dynamic equilibrium with ES, but it is also giving up the releasing enzyme by forming product. And this is the reaction that is forming product, and this is the dynamic equilibrium that it is established with itself. Right? So really, if I say again, so I have a very simple formulation now that my rate of reaction is K2 into ES, and K2 ES is given by this expression here from the KD values, and this is the total expression here. E is either bound, sorry, ET is either free or bound, and the bound fraction is what is making into K2 is making the product, and this is what you have added. So now can you tell me very simply what will be the velocity of reaction? How is ES equal to, what is ES equal to in terms of KD and E1 and S? I just now wrote it out. अभी मैंने ये लिखा यहाँ पे. So what is ES equal to?
So
भाई इसको component इसका
by
component dependent तो कर सकते हैं ना? हाँ. So ES upon, I mean this I wrote just now. From this expression here, this expression, और इसका यहाँ पे. So this is numerator upon numerator plus denominator. So what do we get? Come on. So ES upon ET therefore is equal to okay, go ahead. I'm waiting.
S by KD plus S.
S by KD plus S. So ES becomes equal to this. So now therefore the velocity of reaction becomes equal to what? From here K2 ES, which is ET S upon KD plus S. So you see it's rather simple. Does that make sense?
Oh, yes, sir.
Yeah. So this kind of formulation, this kind of simplistic formulation simplifies the algebra a lot. And I will use this simplistic formulation, and later on I will tell you why the simplistic formulation is not really correct, but allowed. And why it is allowed also I will tell you. Okay, so keep this very simple formulation in mind that V is equal to K2 ES S upon KD plus S. And of course, this K2 ED, this expression here, is really the Vmax. And so you would realize that Vmax of our typical V is equal to Vmax S upon Km plus S formulation. So Km essentially is Kd for all practical purposes. So Km represents the binding dissociation constant, and so the binding efficiency of the reaction. And Vmax is a combination of two terms, the forward reaction rate into the total amount of enzyme present. So actually Vmax changes, as you would have now understood during the practical classes, that Vmax is actually directly proportional to the total amount of enzyme added. Remember, they're very dissimilar from mu is equal to mu max, where mu max is an intrinsic property. You cannot increase or decrease mu max as upon. So monod kinetics and these are fundamentally different concepts. Okay, so they're fundamentally, because they look similar, but they're absolutely different because Vmax is simply proportional to ET. So sometimes we sort of take Vmax and divide by the total amount of enzyme to find out actually this K2 value. We are more interested in what is the intrinsic reaction rate per unit amount of enzyme. Vmax is proportional to ET. The Vmax, more the ET, the more the Vmax. But Vm upon ET is a measure of the catalytic efficiency. So we call that often Kcat. And I will come to Kcat also. So Kcat is nothing but Vmax upon Vmax upon ET, which is nothing but this K2. Am I cluttering up the board too much, or can you see? Hello?
So we can.
Can all of you hear?
We can.
You can see, right?
Yes, sir.
So it is this Kcat, I will put different colors to make it more colorful and cluttered, is nothing but this K2. So this is the catalytic efficiency of the cell, which is Vmax upon ET, because Vmax is a combination of K2 into ET. And Kd is simply Km. So this expression derivation is actually a simplified derivation of the Michaelis-Menten kinetics that we have been talking about. That you just take ES, ES is proportional to E into S, K1, K minus 1, find the dissociation constant, write it in terms of ES and E plus S. So actually, for all practical purposes, I could have not done all this tedious, oh God. Anyway, let me stop here. I'm getting, next class, I will simplify this much more. Instead of doing this complex algebra, we will make a formula for more complicated sets of reactions using this very basic concept of dissociation constant, and then writing the dissociation constant in terms of ES and ES, writing E in terms of ET minus ES, and then you can see that immediately so first writing the KD values in terms of this, and then writing this equation of E total minus ES, and then using this to sort of find out K2 into ES. So it is three-step process. And the third, so by very simple algebra, we can determine most reaction rate constants. Okay. So let us stop here. Okay. So no, next class is Tuesday. Monday we have an exam at 4 o'clock. Just after the lab
Yes, sir.
practicals, 4 to 4:30.
Yes, sir,
Okay.
Yes.
Okay. Okay. One quiz. Okay. Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you.